Hey there, and welcome to the fourth and hopefully final video that I'm going to be making on limits and continuity. So in the last video what we did, you probably might have a little bit of shakiness to you with the work that was associated with it. Hopefully not, but if you did, just bear with me and it'll get better. So in this example, what we're going to be taking a look at first, we have another piecewise function where the domain restriction is at a -2. And what the question we're being asked, for what values of x is this function not going to be continuous, and to justify our answer. So let's take a look at the justification here. All right. Well, the first thing I'm going to see is, well, what are the limits going to look like? So the left-hand limit is going to use the top piece, and when I evaluate that, I get a -1. If I look at the general value of the function, I get a 3, and if I look at the limit from the general limit, oops, I feel like I'm missing, so there we go, missing something on my right hand side. I knew I was looking for something there. So the left hand limit and the right hand limit, first of all, those don't agree with each other. They're not going to approach the same value, so that would indicate that there's a jump discontinuity there. And the general, so the general limit doesn't exist, and the definition that h of -2 is going to equal to a 3, so none of those things exist, or it does not fit the definition of continuity as it's been defined in calculus. So here the justification is going to give us the conclusion that function h is not going to be continuous at x is equal to -2. Now here, again, we're going to be using the definition, the three-part definition of continuity that calculus has given us to create a system of equations, and then to find the values of this piecewise function, find the values of a and b so that the function will be continuous for all real numbers. So we want the piecewise function to be continuous along the linear piece, the constant piece, and the quadratic piece. So the first thing I'm going to do for a problem of this nature, where we want to know what are the values of a and b so that the function is going to be continuous. Well, since a and b have two different variables, or since a and b, the two variables, exist in two different equations, I have to have a system of equations that I can use to find their values. So here I have the equation 2ax minus b is equal to 6, and ax squared plus b is equal to 6. Those are just taken directly from the piecewise function. And they're equal to 6 because that's what that middle piece is. That's what that constant piece is. So at 6, at -1, y will equal 6 at -1. So that's what we have there. So I can take those two pieces, substitute the -1 in there for x and evaluate it and simplify those a little bit. And we don't have the x in the variable anymore, which is nice. So now I have -2a minus, or b, and I have a plus b will be equal to 6. And I forgot the equal to 6 on the left-hand piece. But those are going to be our system of equations. The -2a minus b and the a plus b are really going to be what we want to be working with here. So we're going to take one of those equations, or we're going to take those two equations, set them equal to each other, and I'm going to kind of just put them in a column, one equation on top, one equation on bottom, so that way you can see that we're going to just use the elimination method to get rid of the b variables, solve for a. So when I combine my like terms in the two equations that we have, we work out to be a to be -12. I take that and I can find the value of b to be 18. Now that I have set up the system of equations and I've solved the system of equations, now I can rewrite my piecewise function substituting the values of a and b that we found. And when I do and I simplify it, I get a -24x minus 18 for the first part and a -12x squared plus 18 for the second part. Now I can attempt to find the limit. So looking at the limit on the left-hand side, I get a +6, which is kind of what we wanted, because the middle part says that x is equal to, at -1, y is going to equal 6. So when I substitute it and I look at it on the right-hand side, in the bottom piece of the piecewise function, I still get the same thing. So when I evaluate it at -1, I get a positive 6. So the general limit is a positive 6. So by the definition of continuity, the piecewise function will be continuous as it fits the, I'm sorry, I'm stumbling over my words here. But since the limit of f of x as x approaches -1 is equal to the definition, when I substitute -1 and they both produce a 6, so it's continuous there as long as a will be equal to a -12 and b will be equal to an 18. Now here, this is going to be, I believe, our last example, which is good because we're already at about 5 minutes in a 4-part series of videos here. Now what we're going to be looking at, you know the function value and the limit value can exist independently of each other. Let's summarize the big ideas of continuity on intervals and points on one side to limits. So we have this function g, this piecewise function, and we want to find each of the following pieces. Well, these shouldn't be too difficult to do. Part A is asking us to evaluate the left-hand limit as x approaches 3. Which is pretty simple enough. You can put like, 2.999 in there or whatever, but here it's just simple enough to put in the 3 there. So the left-hand limit is going to show that it's going to approach 7. Part B, evaluate the right-hand limit. And here, again, if you wanted to, you could put like 3.0001, but either way, you're going to come to the conclusion that you're going to approach a 9. So right away, the left and the right-hand limits don't match. So the general limit, I'm going to just go to D here. The general limit doesn't match because the left and right-hand limits don't match. And when I evaluate it for g of 3, I have to use the bottom piece because that's the one that includes the 3. And so 3 squared gives me a 9. So by the definition, is the function continuous? Absolutely not. The general limit and the definition of the function at 3 are not the same. So this function is not continuous. So in summary, a function is continuous at a point, or if a function is continuous at a point, then the function value and the limit value are the same. And that's basically the overall message that we've been repeating over and over and over again, that the general limit and the defined limit at that point have to be the same for the function to be continuous. And that's going to wrap it up for this topic, limits and continuity. I apologize for stumbling over some of my words in this section, but hopefully I didn't lose anybody. If I have any questions that need to be answered, by all means, let me know. Come see me in tutoring, shoot me an email. I'll be happy to work with you. But until then, ladies and gentlemen, thank you for watching. Take care and be well.